purposes. I've played around with it for things like kernel bisection, where you're creating numerous kernel images, booting into them, testing, and then making a bisect decision. So, just to kind of give a quick overview, the name Boom is short for Boot Manager. It's very creative, I know. Now, when I use the term Boot Manager, what I mean there, it's a tool to manage bootloader configuration files. In the Red Hat world, something similar that you may have come across is Grubby. There's a big feature overlap with Grubby. What's different is that we're targeting this thing called the BootLoader Specification, which is a freedesktop.org standard that defines a file and directory structure for bootloader configuration files. It's supported by 2 bootloaders that I know of today, the Grub 2 builds that we ship in the Red Hat distros, and also the Systemd Boot, or used to be called Gummy Boot project. It's a really nice spec in that it cuts away all the legacy bootloader garbage of these huge files and all the entries mixed in. One file, one boot entry. Drop it in. When you're done with it, you just delete it. It's really simple and easy to work with compared to trying to kind of script updates to a Grub 1 configuration file or the rather elaborate system that you have with Grub 2. As I said, snapshot boot is a key focus here, so the tool understands the LVM2 and Btrfs boot notation for that, so it can automatically configure to boot the system into either a Btrfs or LVM snapshot. The focus in the user interface is keeping things simple and defaulting and templating wherever we can. So really the minimum to create a snapshot boot configuration, you've got to give it a title, something to display in the menu, and you need to tell it what device you're booting from. That's it. It'll take your running kernel as the default, figure everything else out from templates, and go and create the file. And we'll take a look at how that works in a couple of minutes. So there's a link there to the spec if you're interested to read further. So, as I said, it's a step towards making bootable snapshots of the system more usable. Other operating systems have had this for years. Solaris with its ZFS, ZFS root pools. It's not a Windows feature, but there are add-on products to Windows that allow you to do that. It's actually worked on Linux for many, many years, ever since Drake-it appeared. But not many people know about it. Even I didn't know. I was kind of messing around with this about a year ago. I just booted a snapshot. There's a few little glitches there. You'll want to be running a recent Drake-it version if you're using the modern thin provision snapshots in LVM. They need an extra flag to make sure they're activated at boot time. But if you're running recent Fedora or say the RHEL 7.5 beta, you'll have all the bits for that. So there's a design document that goes along with this work, and as I said, this is just kind of the first chunk of it, and it's the smallest bit of the overall project. In future, we're looking at extending this to other file systems and also building out a kind of higher level snapshot manager so that you can snapshot multiple file systems at the same time. Hopefully, I'll be coming back next year to talk more about that. So, what do you get when you install Boom? The main thing is the command line tool, the Boom CLI, man 8 Boom to read the docs for that if you're interested. The API, it's all written in Python. The whole thing is Python. Longer term, we may look at re-implementing some of the core APIs in a language like C or maybe even something trendy like Rust. But for now, it's purely Python. There are 4 sub-packages within the main Boom package. One gives you a kind of command-driven procedural interface, which almost exactly mirrors the CLI. And the others, if you pull those in, give you access to the complete object API that Boom uses internally, and you can do anything with that, including delete all of your entries and render your system unbootable. Actually, you can do that with the command line too. There's also a couple of little glue bits, a default configuration that lets you turn things like submenus on, give the submenu a name, or just disable Boom completely if you don't want to use it. So the verbs that the command gives us, create, delete, edit, a couple of different options for displaying things. You can either have them in a sort of tabular report format, a bit like the DM setup and LVS commands and so on, or you can get them displayed basically as the files are formatted. You can also clone and modify existing entries. Again, it's kind of about reducing typing, just as fewer keystrokes as possible to make the configuration. And hopefully, it's reasonably comfortable to use, and if there's time later, I'll give a quick demo of this, either on the command line with the regular tool, or sitting in the Python shell. That gives you the ability to do really large-scale stuff. The kernel bisects that I was doing, I used the shell. You can just set up a simple for loop and just blast out configuration for that. It's probably of more interest to kind of things like QE environments where you're booting up large numbers of images, maybe even some virtualization use cases. On a single system, there's less use for that kind of large-scale automation. In terms of things that we talk about in Boom, there are two really main objects that you'll come across. One is the boot entry. This corresponds to an on-disk entry. It's a single bootable instance of the operating system. Internally, it consists of an operating system profile. It's basically a collection of templates. A boot parameters object that sets things like your root device, your kernel version, and so on. And that spits out via the template mechanism a complete boot entry at the end. Obviously, these go into the BLS loader directory. That's governed by the BootLoader specification. We aim to play nice with other users of the specification. The whole point of having a spec is you can add and remove files there and not interfere with other users on the system. And we're very much pitching this at the moment as kind of like a sidecar thing, an auxiliary mechanism to configure these new boot entries. It won't interfere with your regular kernel updates. It's not going to mess around with your default grub configuration. And as I said, there's a big knob in that file. You can just turn the whole thing off. Okay, so we identify boot entries by a boot ID. We use IDs fairly extensively in Boom to just give things unique handles to refer to. They're not necessarily persistent. So if you change things, the ID might change. The other major object is the OS profile. These are a collection of, well, all of our objects are collections of key-value pairs, actually. It's a bit of a theme. The Boom OS keys define the template. So there are ones for things like your options line. There are ones to form the init ramfs and VMLina's kernel image file names. We store these in the boot file system in a Boom subdirectory. The reason for this is to make them accessible to every instance on the system. If you think about our use case of snapshots, it keeps coming and going, but you may boot into an old snapshot of the system, maybe even before you installed Boom. So if you're going to carry on using the tools, you want all of the configuration data to be available regardless of what instance you booted. And again, we have an identifier for these called the OS ID. That's formed from the data you find in etc OS release. So if your distribution has a unique OS release file, it'll also have a unique OS identifier in Boom. So for example, in Red Hat terms, that means that Fedora 27 Workstation is a different OS ID than Fedora 27 Server Edition, and likewise for the RHEL family. Okay, so just to explain how some of the templating works, to generate the kernel options, this is a fairly typical Boom OS options string. It can be anything you want. You can hardwire exactly what you want and make your own OS profile. But this is a typical one for a modern Red Hat distribution. You can see here we have these substitution keys, % kernel, root device, root ops, and so on. Some of them just expand directly to a string. Things like root ops, it's a bit more fancy. There's a recursive expansion there which includes expansion of the Btrfs or LVM configuration keys. If those are set, then it'll generate the correct string to boot that type of volume. There's a list of keys at the bottom there. They're pretty much what you would expect. I'm not going to read through the entire list. You coming back? Yep. Heading on to the command line, and we'll have a look at this in a second in practice. It's a kind of object-verb type. No, it's not. It's not the cable. I'm getting it on these monitors, and it's just going off up there. The first argument is a type. If you don't give the type, we assume it's the entry because that's the common operation. And then the verb is one from the list here. The verbs for OS profiles and boot entries are exactly the same, so you can perform all of those operations on either object type. And then you set things like the actual values of OS profile keys or the version or whatever you want to set for your boot entry. So let's get a command line. And I'll zoom this in a second so you can see a bit more, I think. So we get the brief help message up there. It lists out all of the available options. You might recognise some of these from tools like DM setup and LVS, so rows, separator, and so on. These control the formatting of the reports that we generate. So if I just list what's on this machine, let me just... so we've got... let's take that back. Oh, I've enabled natural scrolling. This is going to go horribly wrong. So we've got the IDs in the first column, kernel versions in the second. Some of these obviously are fakes that I just use for testing. Then the name of the distribution. If you've got any rel installed, sorry, but your columns are going to go all the way over here. It's just huge. Lastly, we've got the root device. This is the default set of options, of fields rather. If you want to do something different, no, this has gone off now. Oh.
Is that thing doing Is this doing anything?
No, all the screens went off this time, apart from mine.
If it keeps doing, you might have to try VGA, or you think it's... I'll get some assistance. Just do
Okay,
your best.
sure. Okay, so if you do -o help, it'll dump out a list of the available fields. You can see they're grouped by the object type that they refer to. Works exactly the same as DM setup reports. If you ask for a field, we do a kind of join on the data and present it in the row format. You can also do funny things like... no, not on that one. Where did I put that? Oh, I can probably remember it. Dash dash rows dash dash no headings. Helps if you give a command. And put them in the right place. Okay. Oh. I knew I was missing something there. Name prefixes. So this is something you may have seen with device mapper reports. You can dump out all of the data in this kind of shell variable assignment style. So it makes it really easy to pull it into another program, do further parsing on it, and so on. Currently, the report engine is a faithful re-implementation of the device mapper report engine in Python. When I finish another project, DMPY, which exposes the device mapper APIs in Python, we'll move that over and they'll use exactly the same code underneath. But for the moment, it's a Python implementation, so it's missing the fancy selection stuff that my colleague Peter implemented over the last couple of years. But most of the functionality is there. And when we do move to the device mapper engine, we'll also get JSON reports for free, so you'll be able to spit it all out in object notation. Okay, so quick question, because we've got about 10 minutes left. Are we mostly a developer crowd or administrators? I'll focus more on API if it's dev and more on the commands if...
So developers, hands up, and administrators.
That's a pretty even split. Okay, how about a third way? We'll actually have a look at the tool in use and just go through some common operations. So let me go back to my terminal. Hopefully it can pick me up on the mic while I'm sitting down. So let's say one. That doesn't matter. Okay, so this is just a simple little VM running Rel 7. If I do a boom list here, we'll see there's just one entry at the moment. It's actually a bit of a fake one, but never mind. And I'm currently running 310.0693 blah blah blah. And let's have a look at packages installed. I've got an SOS package installed. So if I just do LVS VGS, so I've got a bit of free space in my volume group. I'm just going to create a snapshot now, create the boom entry to boot it, remove a package from the system, that SOS one I just had a look at, and then we'll reboot just to demonstrate what you would actually see. Unfortunately, there's no zoom on Vert Manager, so the text may be a little bit difficult to read when we get to the VM stage, but everything else I can do in the terminal here. So, lv create -s-n root snap -l, say 512 megs, and let's put that in the rel volume group. Okay, so we've now got a new snapshot of the root file system. So all we need to do is enter a new boot entry. So I'm going to do boom create --title before --root lv is rel/rootsnap. And when we create a new entry with boom, it prints it out. You may recognize this if you've touched BLS. It's the notation we'd see in the file there, just exactly as you would find in /boot. Okay, so remember, I'm still running in my main root volume now. So if I just erase the SOS package and reboot the system, this is where it may get a little bit cramped. I'm sorry about that, but it's just the limits of Vert Manager. So I don't know if you can read this line at the bottom, sorry. It says snapshots as the last entry. It's a grub2 submenu. We just pop into there. That's the first one that we saw, Rel 7 snapshot, and down here is our before. I suppose I could have set the resolution really low, couldn't I? That's one for the next demo. Okay, so we're up to a login prompt now. Let me switch back to the SSH terminal. Where did I put it? Let's just zoom that one in. 7. So we're still in the same kernel. It picked up the default that I was running previously. But if we look at the system command line, we can see we've got the root snap as the system root device now. So we're running within the snapshot, and if I query for that SOS package, there it is. This is the before snapshot, so it's preserved the state of the file system and the RPM database as they were there. Okay, so we've got about just under 5 minutes left, so I'll just wind through the rest of the slides quickly. Again, there's more content really than could fit in the slot, but if you see me around the corridors later and there was anything you were interested in picking up, do feel free to stop me. The identifiers are all SHA-2 hashes. We abbreviate them Git style. So what we display is the minimum unique, or 7 if whichever is the greater. All the commands accept the abbreviated form, so you don't have to type these gigantic strings. The command API very much mirrors what we've been seeing at the command line. You have function calls that correspond to the command verbs. depending on which functions you use, say if you used print entries, you'll get a string back, just like you would display on the terminal. If you call list entries, you're going to get a Python list with all the objects inside that you can iterate over. The Object API gives you the full access. So one of the things that's not implemented yet is the ability to override what the template says for certain values on the command line. You can do that with the API, and it will be in the next release of the Boon package. But for now, you have two choices here. You can either use the Object API or create it with the command and then edit it afterwards. But you should only really need that if you're running custom kernels or you have something that really cannot fit into the template system. If you come across a case like that, please let me know, because we'd like to extend it to handle those. Just a very quick, almost UML diagram. So the three main classes, there's a whole bunch more in the reporting stuff, but don't worry about them. Boot entry aggregates boot parameters. It owns that relationship, and it's got an association, a loose shared association to the OS profile that gives the templating strings. In terms of what we're doing in the future, the first one I've already mentioned, allowing you to override and modify what the template generates on the command line. Another part of this project, it's not really part of Boon, but it's something we think is important to allow the full set of use cases, is the ability to allow other file systems to be substituted for snapshot versions. There's quite a bit of complexity involved in that. You're in the boot process, the file system mount process. We've got some functioning prototypes for that, but that's really part of the next phase of the work we'll be getting onto. And the last kind of tier of this is the snapshot manager that allows you to take more coherent snapshots of multiple file systems simultaneously. So before I run out of time completely, any questions? Yeah.
On the boot parameter side, TUB also modifies boot parameters when you do tuning versus computing, right? So how do the two intersect with each other in terms of you repeat?
Yeah, so the question is, TuneD also modifies kernel parameters. How will the two interact? At the moment, they won't. Right now, what you would have to do is to set the template string for the options to whatever TuneD has recommended for your system. It's a single command, and once you set it, it will persist. But right now, there's no automatic sync between them. That's something we're going to tackle in a future version, but there's a real lack of coordination about the whole kernel command line option defaulting mechanism, both within distributions, like the TuneD example, and across them. So it's, for such a simple seeming problem, it's got some hair to it. Yeah. Thanks. Yeah.
Do you plan to expose some functionality for the RPM packages? Because, for example, DKMS modules tend to modify kernel boot parameters. So, any mechanism to correct that?
So the question was tools like DKMS that modify the kernel parameters. Now, I've used, it's a long time since I've used DKMS, but I didn't remember it modifying kernel parameters.
Yeah, for example, NVIDIA drivers.
Ah, okay, yeah. I think that's one, right now we don't address it, but it's another one we'll try and tackle through the same work that we're talking about for TuneD. It's, it isn't in any way standardized at the moment. I'd like to see more of a cross-distribution standard, but it's kind of a new area for me, and I don't, at the moment, know how realistic that is. So we're going to try and accommodate those kinds of use cases. I've got to be honest and say things like TuneD that are kind of fully in the distribution are probably a higher priority than tools like DKMS. I totally understand the need for it, but